Okay, thank you very much, Fernando, for this kind introduction, and welcome to the audience online. I'm very glad to be here and give you this presentation on the potential of actually wide bandgap based industrial inverters and our efforts to develop a research roadmap for that. My name is Andrea Vezzini. I'm professor at Bern University of Applied Sciences, and I'm also a member of the IEA TCP4E, the Electric Motor Systems Platform EMSA. The EMSA is a platform with a total of 15 members, including the European Union, which has as a goal defined to raise the awareness, share information, initiate collaborative projects, and transfer experience to support effective policy development for energy efficient electric motor systems. So the results of our work is geared towards regulators, but also industry, public. And one of the tasks we are working on in EMSA is to look at the international standards for energy efficiency in motors and drives, testing standards, and we coordinate basically also then the policy through policy briefs, the efforts within the community. You see the total 9 members here from Austria, Australia, Denmark, the European Commission, the Netherlands, New Zealand, Sweden, Switzerland, and the US. The output, one of the recent outputs where I was involved was the report on round robin on converter losses, where we heavily with the Industrial Standardization Organization, the IEC, we're working on the testing methods for testing inverters. Together with Sandy Nielsen from the Danish Technology Institute, we were having a round robin for inverters and verified basically the performance of the market surveillance and performance of inverters from 0.12 kilowatt up to 75 kilowatts. This has also been published in as a summary, as an EMSA policy brief, which can be downloaded on the website of EMSA. The current project I want to talk about you is basically our plan for the next 4 years, where we want to have an in-depth look at how can wide bandgap semiconductors actually advance the efficiency for industrial inverters. Is there a business case? Is there a technologically based good application, and which field in the industrial inverter field or large scene is actually good for these type of inverters? For that, probably let's go back a little bit and see what is the motivation on that. As you know, probably most of you, is that the inverter efficiencies are in generally much higher than the motor efficiency, and often we hear that why should we concentrate on increasing slightly the performance of power electronics compared to, for example, the energy efficiency gains you can have with better motors, or as we know there's a lot of potential in the total system efficiency optimization. The one reason I think we should not lose focus on power electronics efficiency is that power electronics is actually everywhere, and especially in the path from generation or production over the transmission, distribution, and then on the end use, you will see not once, but several, up to 4 times probably power electronic stage. And so the cumulative efficiency of these power electronic stages will then be much lower than the individual efficiency. And therefore, it is important to have an eye on it and actually try to reach the highest possible efficiencies on power electronics too, and not say this is not relevant in the system. It might be smaller compared to motors on the drives itself, but the total chain has more than one power electronics. Now, why silicon carbide, or why wide bandgap based semiconductor? inverters. Let's have a quick look at the intrinsic material properties of these semiconductors, and then what are the actually properties which are in the application relevant. You see here a comparison between silicon and silicon carbide power semiconductors, and these are rather technical properties like the bandgap energy or the critical field breakdown voltage, where you can see that silicon carbide outperforms silicon semiconductors factor 3 to almost 10. And these two properties basically are responsible for that you can operate silicon carbide semiconductors with much higher voltage. Very interesting, silicon carbide MOSFET starts 1200 volt, but we see also 3.3 kilovolts, which for very large power applications. So the impact is that we can, these are very, very suitable semiconductor elements for high voltage operation. The saturation velocity as well as the electron mobility are also better or similar, and they're actually responsible for lower switching losses. Especially turn-off losses are very interesting for silicon carbide inverters. And there are secondary effects. If you look at higher switching frequency, this will allow you to actually create or use smaller filters and still reach a low harmonic content in the inverter currents. And finally, we have a much higher thermal conductivity, which lead actually to the fact that we can operate these semiconductors also at a higher temperature, which also will require fewer cooling. And these effects then lead on the end equipment itself to smaller, more compact, more performant, less weighty equipment. While these are the advantages on the system level, we have also some disadvantages in the recent years, which are actually hindering a little bit the introduction of wide bandgap inverters, especially in the industrial inverter landscape. This is the higher cost of silicon carbide chips, which I will address later on. Not that the silicon carbide elements are less reliable, I would say. There is a missing experience on how reliable are. There is a missing experience on how to predict basically the lifetime of silicon carbide elements. And there are, due to the higher power density, due to the higher operating temperature, also different types of failure cases. And we have also, due to the higher switching losses, due to the higher switching speeds, problems which can be arise in the end equipment, the higher, especially the higher change in voltage when switching on and off can have an impact on motor windings, an impact on EMI. The second wide bandgap power semiconductor element is the gallium nitride semiconductor, which himself is, and that's if you compare these two elements, the SiC MOSFET and the gallium nitride transistor, quite different in the sense that one is a vertical element, which means that the current flows from here in bottom to up, and the other is a lateral structure, so the current flows from right to left, which allows, for example, that you can create gallium nitride on silicon substrate, which is an advantage for this type of semiconductors because you could use the silicon wafer technology, whereas in a silicon carbide, you will actually have to grow your own silicon carbide wafer. The disadvantage is that so far it has less higher withstanding voltage. So while silicon carbide excels in 1200 volts and above, we see mainly 650 volt devices for gallium nitride. This is a disadvantage, especially for the 800 volt DC technology, which we will see now more and more in electric mobility applications. But as just recently been shown, there's a possibility to use this type of semiconductors in a novel or in different topologies of power electronics. So instead of a normal 2-level, use a multi-level or 3-level inverter. And with that, you can use actually the 650 volts GaN and reach very high power density, as has been just recently demonstrated. So we have two power semiconductor materials. At the moment, there is a slight advantage for silicon carbide. The market is accepting it faster. There is a bigger acceptance. It's a longer tradition, but due to the advantage of using established production process with the silicon substrate for gallium nitride, there is also a rise of awareness for this type of power semiconductors. And we probably will see both of them reaching maturity in the next years. We already have quite a lot of applications who are accepting silicon carbides and their benefits, especially the automotive market, where Tesla is the first manufacturer is using silicon carbides since the introduction of their Model S and Model 3. We also see now silicon carbide in most of the automotive car applications, especially also for those with higher DC link voltage, and a large part of the Chinese car manufacturers. We see on the battery charging infrastructure, where we see a trend towards 350 kilowatt and higher charging power stations. We see that silicon carbide allows extremely compact power charging stations, which, while the power semiconductor part is actually more expensive, the savings you have because of the smaller footprint of the power stations more can compensate for that. On other applications, we see that especially in big data centers, the distribution of the power supply is more and more actually done via silicon carbide DC-DC converters. We see since a long time quite a large amount of silicon carbide-based solar inverters, and there's also more and more in the circuit protection transmission part. But we haven't seen a lot of change or a lot of acceptance in the industrial inverter drive application. And on one hand, this is surprising because, as you can see here, if you look at the timeline of improvements of industrial-based inverters, we see that every time there was a new technology, being it from silicon-controlled rectifier to transistors, or from transistors to high-speed transistors, then IGBTs, there's an adaptation in the market, and there was always the trend towards higher efficiency. Currently, but we see now there's a market saturation since about 2003. We reach about 97% of efficiency with IGBTs, and there is quite some resistance to introduce silicon carbide. One of the reasons is often also here in the presentation done also by CMAP representatives, is that there is the argument that with the existing IGBT technology, there is an optimum between cost and efficiency. So we reach about 97.5% efficiency with the drives at minimum cost, and there is a steep incline in cost if you want to reach only a small amount of higher efficiency. Whereas with motors, for example, you can get more efficiency gains with less costs given by the smaller inclination of this curve. This has been a long time argument, which with the decrease of costs for silicon carbide and the additional benefit of cost savings, which can be realized with silicon carbides in the auxiliaries as well as the filters input or output, is getting less and less traction. The other argument has been always that there is not enough experience regarding reliability, and that industrial inverters are very, very critical regarding this fact. So this was actually the reason or the origin why EMSA decided for the next period to look at the challenges and criticisms towards silicon carbide inverters or wide bandgap inverters for industrial drives. So we want to also include gallium nitride, but we want to actually get a better understanding why some sectors like the automotive sector have fully embraced silicon carbide and why the industry sector has basically not opened the door at all for silicon carbide. And during a workshop organized by EMSA, we identified basically 5 reasons, which I now, during this presentation, I'd like to present to you. One is the high initial component cost. So we're talking about the higher cost of silicon carbide semiconductors compared to IGBT or silicon-based semiconductors. The other one is application readiness, so the availability, the volume of the numbers of different suppliers. System design and implementation complexity, as a new power component, will require also different designs, not only on how to drive the power semiconductors, but also regarding cooling, filters, reliability and durability concerns. So we don't have the same experience as with silicon. So that's one of the bigger concerns here. And then the risk to equipment is also always cited as one of the hindrances. If you want to go now for point of point, as I said, the high initial cost is really a significant barrier for adoption when the application cost is a critical factor. And in most industrial application, especially the investment at the beginning is regarded as critical. And so it's very important to actually have a look at the detailed analysis of the costs. Look if over a life cycle of the inverter, the efficiency advantage of an inverter will not bring also a cost advantage. And so one of the outcomes of this that we have to demonstrate that the energy savings which you can achieve are actually compensate for the higher initial cost. And let me explain this a little bit more in detail here by just showing you. If you look at 1200 volt power semiconductors, this line here, the blue one is based on IGBTs from Infineon in that case. This is some cost comparison. You can see that with higher current density, there is more or less a linear relationship between the price as well as the current capacity. If you look now on the silicon carbide market with the 4 biggest, let's say, competitors there is a range there where you can see, which also allows a more or less a linear approach. But what we see is basically that there is a price difference between, easily can go from 2 to 3 times today, and on that slide might be even a little bit higher. So that's on the component or on the device sector. So as a first approach, we could say, okay, let's see if we take a typical module, how it's used in inverters. So this is a silicon-based typical 3-phase inverters, 1200 volts, 35 amps. It has the semiconductor based on silicon, and it has also the diode on silicon. You can compare this now with 2 full-SiC modules. Full-SiC meaning that here we got 6 silicon carbide MOSFETs, no diodes, using the internal body diode of the silicon carbide MOSFET, or as a full silicon carbide module where also additionally we have some silicon carbide diodes. As you can see, this is a 35 amp, these are 25 amp semiconductor elements. These are available, and the comparison now is based on the following difference. Here you can see basically the voltage drop across as you see here, this is the voltage drop across the power element with the forward current. And the blue line here is the voltage drop across the silicon carbide at 25 degrees. And as you can see, for a given current, you have a very low voltage drop. The same current at the IGBT level, that's the red line here, will give you more than 1.5. So we have like double the forward voltage drop. So for conduction at lower currents, this is definitely an advantage for silicon carbide. But as you can see, the voltage drop here for the silicon semiconductor actually will getting closer to the silicon carbide element, and it's probably crossing here somewhere at currents at 85. What is more important is that there is a silicon carbide positive temperature coefficient, so that it means that with higher temperature, and this dashed line is at 150 degree, you can see that there is a turning point, which is here straight at about 40 amps, where the IGBT actually has a higher current capability than the silicon carbide. What does it mean? It means basically, especially in the low load or partial load, where you have lower currents than the nominal current, you will have a very good performance of the silicon carbide MOSFET, whereas at nominal current, they, especially at higher temperature, which will happen anyway, if you operate at nominal load, you will have more or less equal conduction losses. If you look at switching losses, we see that the switching losses are very low compared to silicon. The question here is, should you use full SiC without external SiC Schottky barrier diodes, or should you use additional SiC diodes, which is a cost criteria? But as you can see that the internal body diode in the SiC MOSFET has quite first of all, a very high forward voltage. So it means that you have to switch on the silicon carbide MOSFETs and let it reverse conducting. But what is more important, it has still a little bit of reverse current. So adding a very fast additional SiC diode here will reduce the losses. So while silicon carbide has very, very low switching losses, it's even better to have anti-parallel or freewheeling diodes also based on SiC to have even less losses. How does it translate? Now we compare basically our full SiC mini-skip module with the silicon mini-skip. And we have here two slides. As you can see, this is the maximum output power. The blue line is the silicon-based, and you have here over switching frequency. Now, having higher switching frequency means that you have a lot of switching, or the switching losses will increase as a function. Therefore, when you have a fixed amount of losses, if you have high switching losses, you have to reduce your conduction losses. Therefore, the output power will also decrease. When you look now at full SiC, the red line is without the diode, the black line is with the freewheeling diode. As you can see, it's a better performance. And as we see, the impact of the switching losses is much less. And especially, as you can see then, at higher frequency, we have an advantage of the silicon carbide modules. This advantage on total output power, basically for a given loss amount, is translated directly into efficiencies. As you can see, when we are at very low switching speeds, like 4 or 5 kilohertz, there is not such a big difference between these two semiconductor devices. But as soon as you increase the switching frequency, we see a decrease in efficiency. and we therefore have then an advantage of silicon carbide. Again, the silicon carbide module with the freewheeling diode has a slightly better efficiency. So what we get from this is basically silicon carbide allows us apparently to increase switching frequency without too much penalty in losses. And this is something which is shown here a little bit. So compared to a 5 kilohertz switched silicon inverter, where you have roughly same amount of switching losses and conduction losses, if you run the same inverter now with a silicon carbide module with a freewheeling diode also on silicon carbide, we have a reduction of almost 50%. Because the switching losses really go down compared to silicon. And therefore, we can go then higher again with the frequency, and we'll still reach slightly smaller or similar losses. Now, what's the advantage? We'll see this in the following example here. A typical application is a pump here, where you have a quadratic torque curve over speed. This is a roughly a 50 kilowatt application here, and we want to use a drive which has a switching frequency of 5 kilohertz, where the voltage switching speed is limited to 5 kilohertz per microsecond. This is typical silicon-based drive. And we actually going to replace basically here now the output drive with a silicon carbide MOSFET, where we have the following limitations. We keep basically the switching speed to the same speed, so the 5 kilovolts per microsecond. I will see later on what does mean. And we don't increase the switching frequency to basically limit the leakage current. So basically, it's just a plug-in replacement. So we'll have a much better efficiency, as we have seen, because we have same switching frequency. And especially in part load, there will be an advantage. And this is seen here, as you can see, the fixed line, these are the losses. So the difference between gray, that's the IGBT, and red, that's the silicon carbide, can be between 40 and 80%. Sorry, between 62 and 54%. So quite half of the losses, which has an impact on the boost of efficiency, which is between 1.7 or 0.8 better, depending on the operation speed. Now, the operation speed, keep in mind, is also has a lower torque when you have lower speed. Now, if this would be applied now to a typical 15 kilowatt drive, this would mean that the total losses will be reduced from 356 watts and the nominal point down to 270 watts. And at some lower speeds, we will have also between 11 and 24%. We also have 11% of reduction in losses. Now, you have to take this and look at the mission profile, and this is probably the most important part. If you have a variable speed drive application, we need to look at the different operating speeds and how much time you go. So you see here, this is the operation time over a year. It roughly is between 40 to 100%, with the largest part between 60 and 70%. And if you take this into account, you have to then look at the efficiencies at these different speeds, look at the energy which is turned over at these speeds, and look at the savings you have, multiplied with the electricity cost in Germany in 2021, which is 0.26 euro. You would have then total annual accumulated losses, and you have this for silicon and silicon carbide, and you have a reduction of roughly 55%. Meaning, because especially in the part load range here, we have efficiency gains, we can then look at these gains and see what did we actually save. If you look at that, these 354 kilowatt hour savings multiplied with the 0.26 euros per kilowatt, will give you then a payback in less than 1 year. On the other hand, looking at the initial component cost can be compensated by energy saving costs, and the payback is very, very short. On the application readiness side, it's the problem which most of the manufacturer of inverters is that how good is the production capacity and the availability of these wide bandgap components compared to their silicon-based counterparts. There's a certain risk that there could be a supply chain challenge, because especially as now large parts of the production is apparently going into the automotive business. We see that the power electronics market is growing very fast, but actually the silicon carbide market will outperform the silicon market by a factor of 3. And this is pushed especially by industrial segments like PV in data centers and photovoltaics, and also, as you can see here, especially by the automotive industry, where we already are at about 73%, or which will be even higher. Now, it means that as we foresee a large increase in demand, there is also clear that the silicon carbide industry has started to heavily invest in increasing the wafer and device manufacturing capacity. And one of the key, let's say, points here is that there is a move from the wafer size 6-inch, which is 150 millimeters, to 8-inch. And while this is a relatively small, if you say so, size increase, the increase in die sizes which you can put on that surface is almost doubling. So that's a 90% increase. And that gives us a much better yield. The usable area has increased, and the cost advantage is very high. So there are some companies who have completely now switched to 8-inch. Wolfspeed is one of these companies, and they have faced, on the other hand, also some challenges. The challenges are that when you grow silicon carbide on an 8-inch wafer, you will have a thinner boule, basically less output, which additionally then when you're cutting it, it's very difficult to cut it to the same slice thickness as in a 6-inch application. So again, the yield, or let's say, of this boule is even decreasing. Apparently, this has been solved now, and they're closer to 350 than they've been to 500. But on the other side, as you can see here, that this is their problem. They have, by changing now from 6 to 8-inch, they're starting again with the yield optimization. They're starting again with the defect optimization. And apart from Wolfspeed, some of the bigger players are still a little bit waiting on investing, because the transition is a big issue. But in the coming period, we certainly see this move. This is also a little bit pushed by a quick rise of Chinese manufacture of silicon carbides, given by the demand of the local market. More than 60% of the electric cars now are sold in China alone, which means that there's a big market of doing. But for the other players, it's quite a problem, because in Europe especially, the battery electric vehicle demand has been lower than expected. So it means that while on one side they have a high investment of time, money, and resources, with the technology change to 8-inch, they have a lower revenue than expected. And therefore, we see an overcapacity, and we see a price erosion, and we see a push towards other industries. So we might see that industrial inverters become interesting for some of these suppliers. They are under a heavy pressure because their capex is actually much bigger than the revenue at the moment with all the transition they're making, and it's expected that the capex will be smaller than the revenue only starting 2027 or later. This line could be even going. So at the moment, the industry is facing an issue while they building up the capacity. And if you're building up capacity and you don't have the amount of customers in one sector, you try to get into the other sector, and that might be an opportunity for industrial inverters. One of the third key factor which we have identified is the system design and implementation complexity. The question is, which topology should we choose? Is the two-level versus multi-level, but also is there an impact on the thermal management systems? Do we need specialized design and application knowledge, especially on the system level regarding protection circuits, filters, and so on? And as a quick example here regarding the potential for the filter design, if you look at a active front-end inverter, not only you have an output inverter for the motor drive side, but you have also an active inverter on the line side, the grid side. This will allow you power flow in both directions, and it will allow you to also have very low harmonic distortion on the line side by having sinusoidal currents on the input. Typically, such low harmonics active front-end inputs, they operate at a carrier frequency of 5 to 6 kilohertz and use additionally large LCL filters for the line side. They're either embedded or as a separate unit. For an example of such a active front end where you have this is about a 22 kilowatt, so it's 400 volt line-to-line voltage, 30 amps RMS current. In a silicon-based inverter, you would switch with 5 kilohertz, and with a silicon carbide, you would go up to 20 kilohertz. Remember what we saw before, increasing the switching frequency will not have such a big impact on the total losses of the silicon carbide. But now the impact, as you can see here, will be not so much in the total system losses. So as you can see, I'm operating silicon modules at 5 kilohertz with 247 total losses from the semiconductors, whereas the silicon carbide modules, which operates 4 times higher at 195. So you could even go a little bit higher with the switching frequency. The big advantage now is if you look at what happens on the filter side, going from a 5 kilohertz input switching frequency to a 20 kilohertz switching frequency means that you can reduce the size of these filter reactors here from more or less like 75% for the grid input side, or for the inverter side, so the motor side, or 47 on the grid side. And that means that you have also quite a high reduction in weight from 19 to 10 kilograms, and you have also a reduction in losses. And this means that you can do actually smaller inverters. You don't have this heavy weight in the inverters. The volume, the size of the packaging will also be smaller, which gives you an advantage in storage, in transportation, and also material use. So that's just by having more or less the same efficiency on the inverter side, but by increasing the switching frequency, you get less noise, you get better efficiency, you get a more compact machine at a comparable cost. And to close now the last 2 points, I will go a little bit faster on the reliability and durability concerns. As I said, there must be more research done in the future to actually do a better prediction on the failure modes as well as the lifetime of the semiconductors. And this has to be actually then supported by some accelerated life cycle testing. And this is certainly a topic which will be interesting in the next 5 years. And the last point I want to mention here is actually risk to equipment. Often this is also mentioned, especially regarding the high switching speeds, that there is a risk to the equipment, that there might be damage to the motors which are driven by high switching speeds. And if you look at the two main, let's say, factors which can happen, or two main failure modes which can happen, we see that the higher switching speeds will or could lead to winding insulation failures because you would have additional higher over voltage. The second point is the additional bearing currents can lead to damages on the bearings. It was a similar discussions we had about roughly 40 years ago by the introduction with the IGBT semiconductors. But as you can see here, naturally the switching speeds on silicon carbide is again much faster than with the silicon ones. So all the technology advancements which have been done on the insulation properties for IGBT-based inverters has now to be re-questioned and seen if this is also possible for the switching speed of silicon carbide. The switching speed will lead to over voltages, and this over voltage is heavily dependent on cable lengths and filtering at the output of the inverter. So we could actually have some filters directly at the output of the inverter and therefore decrease the impact, or without filter, the cable length is basically the most important factor. From our testing here, this is a very short cable length, the silicon versus silicon carbide, with switching speeds where we have like 5 or 6.7 kilovolts per microsecond for the silicon and about 18 kilovolts for the silicon carbide. You see that for a short cable length, the over voltage for the silicon carbide can be much higher than the one for the silicon based. But what is important is as soon as you go for a cable length which is over the critical cable length, you will see over voltage in both cases. And they reach the critical value, which is about 2 times the DC link voltage. So if your application is actually already on a longer cable length, this is not the issue in that sense. Where we want to have actually proof of that, we do some accelerated aging testing. And this is a test setup we have here. We have a silicon carbide inverter and we have a silicon inverter. The silicon inverter drives the motor and silicon carbide then drives the brake, and you have a circle here, and we do periodic aging measurement using partial discharge inception measurement, where we actually try to find out if with more and more aging of the insulation, we have more partial discharge. Partial discharge, you can see here, this is the small current here. And we are using then a high bandpass filter to detect this. This is an ongoing test in our lab. Another ongoing test is the impact of the high switching speed or the common mode voltage supply, the switching speed of the common mode, which will have an impact on the bearing currents, and the bearing currents then will have problems creating basically grooves inside the bearings, and the impact can be seen there. And we actually are measuring these by adding some Rogowski coils inside the end shield of the motor to detect how much impact we have from this. Now, as you can see, some examples here, and to finish basically this presentation of the ongoing, well, let's say that the burning questions on what is the hindrance of the adoption of silicon carbide into industrial inverters. we came then up with that we want to actually do a survey. We want to look at all the ongoing research. We want to basically collect and document these activities, especially with a focus here in Switzerland, between the period of 2025 to 2029. And we want to document these at the end of this period in some sort of white book. We have therefore actually then created basically this roadmap where we say, okay, what are the 4 research questions? As you see, the application readiness. This includes the cost point, the design and implementation. As you have seen, this is what is the best way to use silicon carbide semiconductors. Then the reliability and durability is a big question here. We would like to have a look at what is the state-of-the-art prediction. How good can you actually say that certain operating strategies will have an impact on the lifetime? And then the risk to equipment, as we said, now we want to have a better look even more on the impacts on bearings and insulation aging, EMC testing and EMC measurement, but also the question, can we measure correctly wide bandgap inverters? This is all questions which we are collaborating with different universities in Switzerland, but also Germany and Denmark will contribute. We will try to document and then possibly in 2029 publish this in a white book for everybody. And so I'm actually 2 minutes over the 45 minutes Fernando promised me. I hope this is okay, and I'm open for questions. Thank you very much.